What if everything we see, the stars, the galaxies, the vast emptiness of space, is just the surface of something far deeper? Picture standing at the edge of an ocean, watching the waves ripple under the sun, unaware of the strange and luminous creatures hidden in the abyss below. That's where we are right now with our understanding of the universe. We've mapped the visible cosmos, traced the dance of galaxies, even glimpsed the afterglow of the Big Bang itself. But beneath it all, there could be layers of reality we've barely begun to fathom, hidden structures, unseen dimensions, forces and geometries so alien they defy imagination. This isn't science fiction. It's the cutting edge of cosmology, where physicists and astronomers grapple with questions that sound like riddles from an ancient myth. What if our universe is just one bubble in an endless cosmic foam? What if space itself is woven from threads we can't perceive, or shaped by echoes from other realities? For decades, these ideas lived on the fringe, wild guesses scribbled on chalkboards. But now, thanks to breakthroughs in mathematics, simulations, and mind-bending observations from telescopes like James Webb, these theories are stepping into the light. Some might hold the keys to mysteries that have haunted us for centuries: dark matter, dark energy, even the origins of existence itself. That's where this journey begins. Over the next 30 theories, we'll peel back the layers of the cosmos like an onion, each revelation more startling than the last. Some will feel familiar, like the holographic principle, the idea that our three-dimensional universe might be a projection from a two-dimensional boundary. Others will stretch the limits of belief, like brane worlds colliding in higher dimensions or time itself being an illusion. But here's the beautiful part: you don't need a physics degree to wander these frontiers. We'll use everyday analogies. Think of space as a loaf of raisin bread expanding in the oven, or gravity as dips in a stretched rubber sheet, to turn the unimaginable into something you can almost reach out and touch. So settle in. By the end, you might never look at the night sky the same way again. Let's start with a theory that turns reality inside out, literally. The holographic principle suggests that everything we experience in three dimensions, the stars, the planets, even your own hands, might not be what they seem. Instead, this wild idea proposes our entire universe could be a projection, like a cosmic movie screen, with all the real information encoded on a flat, two-dimensional surface at the edge of space. Think of it like a credit card hologram. Tilt it, and a 3D image appears, even though all the data is stored on a thin, flat strip. This idea didn't come from nowhere. It grew out of a puzzle about black holes. In the 1970s, physicist Jacob Bekenstein discovered something bizarre: the entropy, or hidden information, inside a black hole isn't proportional to its volume as you'd expect. Instead, it's tied to the surface area of its event horizon. That's like saying the contents of a library don't depend on how many books are inside, but on the size of the front door. Leonard Susskind and Gerard T. Hooft took this further, arguing that if a black hole's information lives on its boundary, maybe everything does. What's mind-blowing is how this flips our understanding of space. We've always assumed reality is built like a block of marble, solid, tangible, with depth. But the holographic principle whispers that space itself might be an illusion, a kind of shadow cast by deeper, flat physics we can't yet see. Even stranger, this isn't just philosophy. Advanced math and string theory calculations support it, suggesting that the fabric of the cosmos might really be a kind of cosmic ledger, with every event, every particle, just an entry on a vast, hidden spreadsheet. So why can't we tell? For the same reason you don't feel pixels when you watch a movie. The resolution is too fine. If the universe is a hologram, its pixels would be unimaginably tiny, far smaller than anything our tools can detect. But if this theory holds, it could rewrite the rules of reality, merging gravity and quantum mechanics in a way even Einstein couldn't imagine. And that's just the first stop on this journey. Now imagine the universe not as a smooth, unbroken canvas, but as a tapestry riddled with tiny, frayed threads, cosmic strings, remnants of the violent symmetry breaking that shaped reality in its first fleeting moments. These hypothetical filaments, thinner than a proton but stretching across entire galaxies, could be lurking unseen all around us. Picture space as a frozen lake. When water turns to ice, microscopic cracks form. In the same way as the newborn universe cooled, defects might have formed in the very fabric of space-time, leaving behind these bizarre, ultra-dense scars. Unlike black holes or stars, cosmic strings wouldn't be made of matter. They'd be pure geometry, kinks in the structure of space itself. If one passed through this room right now, you wouldn't see it, but you'd notice something impossible. A pair of scissors left on a table might suddenly slide together without being touched. That's because strings warp space so intensely, they create what physicists call conical singularities. Think of it like stitching a thread through a bedsheet, then pulling it taut. The fabric puckers around the thread, altering the shortest path between 2 points. For us, that means light bending, time distorting, and objects moving in ways that defy Newton's laws. But the strangest possibility, cosmic strings might form loops that vibrate like guitar strings, rippling space-time with gravitational waves. Some theories suggest these vibrations could be so extreme, they'd pinch off segments of space, creating closed time-like curves, a fancy term for wormholes that might, just might, allow travel backwards in time. It sounds like something from a pulp sci-fi magazine, but the math checks out. In fact, Nobel laureate Kip Thorne once showed that 2 strings moving past each other at near light speed could warp space into a time machine, though you'd need infinite energy to steer it. Here's where it gets eerie. In 2007, astronomers spotted a bizarre cluster of galaxies arranged in a perfect ring over 10 million light-years wide. One explanation, a cosmic string might have slid through, compressing matter in its wake like a wake behind a boat. And if string theory is correct, these filaments could be crisscrossing the cosmos like spider silk, shaping the large-scale structure of everything we see. We haven't caught one yet, but next-generation telescopes hunting for telltale flashes of light or sudden jumps in atomic clocks might finally prove we're living in a universe threaded with these ghostly defects. And if they exist, they'd be fossils from the universe's first trillionth of a second, a time before atoms, before light, when reality itself was still knitting its first stitches. What if our universe is just one page in an infinite cosmic book? That's the startling premise of brane cosmology, a theory that reimagines reality as a floating membrane or brane drifting through a higher dimensional space we can't see. Forget the Big Bang as a single explosion. Picture instead 2 of these colossal branes, each holding entire universes, colliding like symbols in the dark. The energy of that impact could have sparked everything: space, time, even the laws of physics themselves. This idea turns traditional cosmology on its head. Instead of a fiery singularity birthing the cosmos, brane theory suggests our universe might be one of many layers, like sheets of paper stacked in a realm with extra dimensions. Imagine living on the surface of a soap bubble, completely unaware of other bubbles floating nearby. That's us, confined to our 3-dimensional brane, blind to the larger, bulk space around it. But here's the twist: gravity, unlike light or matter, might not be trapped here. It could leak into those higher dimensions, which would explain why it's so weak compared to other forces, like hearing music through a wall, muffled and faint. The real fireworks come when branes collide. Some models suggest these crashes aren't one-time events but cyclical, happening over and over across eternity. Each collision resets the cosmos, triggering a new Big Bang and erasing the old universe. It's a cosmic reboot with energy from the impact stretching space, seeding galaxies, and perhaps even imprinting patterns we see today in the cosmic microwave background. Remarkably, this could solve one of physics' biggest headaches: why the early universe was so perfectly tuned for life. If brains have been colliding for eternity, eventually one would hit the cosmic jackpot, conditions just right for stars, planets, and us. Critics argue it's untestable, but there are tantalizing clues. If gravity really leaks into higher dimensions, subtle anomalies might lurk in how objects orbit or how gravitational waves ripple. Future experiments measuring gravity at microscopic scales or hunting for echoes of pre-Big Bang events could tip the scales, and if brains exist, they might not be alone. Other universes could be hovering millimeters away in a dimension we can't perceive, their particles and forces forever out of reach. It's a humbling thought. Everything we know might be just one island in an ocean of unseen realities. Now consider this: every choice you've ever made, what to eat for breakfast, whether to turn left or right on a walk, might have spawned an entirely new universe where the other option played out. This isn't just a thought experiment, it's the spine of level 1 of the multiverse theory, where reality isn't a single thread but an endless tapestry of parallel worlds, each born from quantum randomness. Imagine flipping a coin. In our universe, it lands heads, but according to this idea, at that exact moment, spacetime splits like a branching river, creating a new universe where the coin landed tails, and another where it balanced on its edge, and another where it vanished into thin air. The math behind this is less sci-fi than it sounds. It springs from quantum mechanics, where particles exist in superpositions, multiple states at once, until observed. The infamous Schrödinger's cat, both dead and alive in its box, that's not just a paradox. It's a blueprint for reality's hidden structure. What makes this more than philosophy is its marriage with cosmic inflation, the theory that our universe ballooned from smaller than an atom to cosmic size in fractions of a second. Inflation doesn't just explain why the cosmos is so uniform, it suggests the process might never have stopped. Instead of a single Big Bang, picture an endless foam of universes bubbling into existence, each with its own laws of physics. Some might have stronger gravity, ripping stars apart at birth. Others could be so dark and cold that atoms never form. But here's the kicker: in an infinite multiverse, every possible configuration of particles must exist somewhere. There's a version of you reading this in a world where dinosaurs never went extinct, and another where Earth orbits a blue sun. This solves one of cosmology's greatest riddles: fine-tuning. Why do constants like the strength of gravity or the mass of an electron seem perfectly calibrated for life? If countless universes exist with random parameters, it's no surprise that at least one got lucky. We're not in a designed universe, we're in the lottery winner's universe. Critics argue it's untestable. How do you observe a reality forever out of reach? But clues might lurk in the cosmic microwave background. If our universe once brushed against another, it could have left faint bruises in the afterglow of creation. Others suggest that quantum entanglement, spooky action across distances, might be shadows of deeper connections between worlds. The real mind bender. This is just the first level of the multiverse. Some theories propose layers upon layers, like Russian nesting dolls of reality. But for now, the level 1 multiverse offers a humbling thought. Every moment of uncertainty isn't just a fork in the road, it's the birth of a new cosmos. But level 1 is just the beginning. What if entire universes, not just timelines, are bubbling into existence all around us, each with its own physics, its own stars, and perhaps even its own strange forms of life? Welcome to level 2 of the multiverse, where the cosmos isn't just branching, it's boiling. Picture a pot of water on the stove. Before it boils, the surface is still. But as heat rises, tiny bubbles form, expand, and pop. Now imagine space itself is that pot, forever simmering with energy we can't see. This is eternal inflation, a theory that says our universe isn't the only bubble, it's just one of countless others, each pinched off from an endlessly inflating cosmic foam. And here's the wild part: inside each bubble, the laws of physics might be completely different. One could have gravity 10 times stronger, crushing matter into black holes instantly. Another might have no weak nuclear force, leaving stars unable to shine. The engine behind this cosmic champagne is something called the inflaton field, a kind of invisible energy that stretched space faster than light during the Big Bang. Most of this field keeps expanding eternally, but pockets of it can lose energy, like steam cooling into water droplets. When that happens, inflation stops in that region, and a new universe crystallizes out of the chaos. It's like a forest where mushrooms pop up at random, each one a self-contained world, forever sealed off from the others by walls of still inflating space. This solves mysteries level 1 can't touch. Why is our universe so finely tuned for life? Because in an infinite froth of bubble universes, some will inevitably hit the cosmic jackpot. Others might be barren wastelands or collapse instantly. We just happen to live in one where the numbers lined up, and there's a haunting beauty to it. Beyond our cosmic horizon, there could be realms where light moves slower, where time runs backward, or where space has 7 dimensions. Some physicists even speculate these bubble universes might collide. If 2 bubbles brushed against each other, the shockwave could leave scars in the cosmic microwave background, strange circles of hot or cold spots where the boundaries touched. We've seen odd patterns in the sky that might fit, though the evidence isn't conclusive yet. Either way, the idea reshapes our place in reality. We're not just one universe among many, we're a single raindrop in an endless storm, falling through a night filled with other drops we'll never see. Now let's peel back another layer of the multiverse, one where reality fractures not just across space or time, but with every single quantum flicker. This is level 3, the many worlds interpretation, and it turns the tidy world of cause and effect into something far stranger. Forget parallel universes born from cosmic inflation or branching timelines here. Every possible outcome of every quantum event spawns a new reality. It's not just that there's a world where you took a different job or missed your train. There's a world where your coffee cup quantum tunnels through the table, where dinosaurs evolved opposable thumbs, and where the laws of physics themselves twist in ways we can't even name. This idea didn't come from a sci-fi writer. It erupted from the equations of quantum mechanics in the 1950s, when physicist Hugh Everett stared down one of science's great paradoxes, the Schrödinger's cat problem. You know the thought experiment, a cat in a box poisoned by a quantum-triggered device is both alive and dead until someone looks, but Everett asked, what if the observer splits too? In his vision, the moment you peek inside, the universe divides. One version of you sees a purring cat, another steps into a nightmare. No collapse, no single outcome, just an endless tree of possibilities, each branch real, each untouched by the others. What sets Level 3 apart from the multiverses we've seen? Level 1 gave us infinite copies of our universe in space. Level 2 gave us bubbles with alien physics. But Level 3 is personal. It suggests that right now, as you watch this, your consciousness is riding just one thread in a tapestry of infinite yous, each living out every conceivable variation of this moment. The coffee you didn't spill, somewhere it's pooling on the floor. The word you bit back in an argument, another version of you is still shouting it. And every quantum event, every electron spin, every photon's path adds new forks in the road. Critics call it extravagant, but the math holds up. Unlike other multiverse theories, many worlds doesn't invent new physics. It simply takes quantum mechanics at face value, no hidden variables, no wave function collapse, and it solves a deep mystery: why we only ever see one outcome when particles exist in superpositions. The answer: we don't. Every outcome happens, we're just blind to the others. Here's where it gets eerie. If many worlds is true, there's a version of you who just disproved it. Another who won a Nobel Prize for confirming it. And somewhere, in a universe where quantum flukes stack just right, a version of you is reading these words in a language that doesn't even exist here. The theory doesn't just reshape reality, it dissolves the idea of what might have been into what is somewhere. And that's the ultimate cosmic gut check. Not only are we not alone in the universe, we're not even alone in our own choices. Level 4 of the multiverse takes us beyond branes, beyond branching timelines, even beyond quantum possibilities, into a realm where reality isn't just governed by math but is math. This is Max Tegmark's radical vision, a cosmos where every coherent mathematical structure isn't just a tool to describe the universe, but a universe unto itself. Picture a library where each book isn't about a world. It is that world with its own physics, its own dimensions, its own raw logic. In this view, our universe isn't special because it exists. It exists because it's one solution in an infinite sea of equations. The leap here is staggering. Earlier multiverses, bubbles, branching worlds still played by loose rules, space, time, causality. But level 4 throws even those out. A universe here could be a four-dimensional fractal, a topological knot where time loops like a Möbius strip, or a void where 2 plus 2 equals 5. If it can be described mathematically without contradiction, Tegmark argues, it's out there, physically real, humming along in some abstract corner of existence. Our cosmos, with its quarks and quasars, just one entry in an endless catalogue of mathematical possibilities. Critics push back hard. Is this science or metaphysics? After all, how do you test a universe built from equations we can't observe? Tegmark's answer cuts deep. Maybe we already have. The shockingly precise fit between math and reality. From the spiral of galaxies to the flutter of a butterfly's wings hints that math isn't just a language we invented. It's the scaffolding of existence itself. Einstein once marveled that the universe seemed comprehensible. Level 4 takes that awe further. Maybe it's comprehensible because it's mathematics in disguise. Here's where it gets trippy. If every consistent math structure is real, then somewhere there's a universe where Shakespeare's plays are encoded in the digits of pi, where the Mandelbrot set breathes as a living landscape, or where gravity follows not the inverse square law, but an equation we've never dreamed of. The boundary between physics and philosophy blurs. Is the multiverse a prediction of science or a metaphysical stance? Tegmark admits it's both, a hypothesis so vast it reframes what reality even means. Yet there's a haunting elegance to it, no fine-tuning problem, no special pleading, just the cold, beautiful consequence that math, left to its own devices, spawns all possible worlds. And that leaves us with a cosmic joke. The ultimate theory of everything might not be a single equation, but the realization that every equation is a universe waiting to be lived. Somewhere beyond the edge of the observable universe, something massive is pulling. Not just a galaxy or two, but thousands of them, entire clusters racing through the void at speeds that defy logic, all streaming toward some unseen attractor like moths to a cosmic flame. Astronomers call this phenomenon dark flow, and it's one of the most baffling discoveries in modern cosmology. Picture throwing a handful of leaves into a river. Most drift randomly, but if you notice them all sliding toward one bank, you'd suspect a hidden current. That's what we're seeing, except the river is space itself, and the current has no visible source. This isn't just a slight statistical quirk. Studies of galaxy clusters using the Wilkinson microwave anisotropy probe and Planck satellite revealed something staggering. Over 1,400 galaxy clusters, some billions of light-years apart, are all hurtling in the same direction at nearly 2 million miles per hour. That's fast enough to cross the Milky Way in a cosmic blink. The kicker, there's nothing in our observable universe big enough to exert that kind of gravitational pull. No supercluster, no wall of galaxies, not even the theoretical Great Attractor can explain it. The force seems to come from beyond the cosmic horizon, the farthest light we can see. One spine-chilling possibility, the pull might originate from another universe. In bubble multiverse models, if our cosmos bumped against a neighboring one during inflation, the gravitational tug of that other bubble's mass could still be yanking on us like a magnet under a table dragging paper clips. Even stranger, some simulations suggest dark flow could be a scar from the Big Bang itself, a cosmic lopsidedness imprinted when spacetime first exploded into existence. Imagine baking a loaf of bread with a pocket of air trapped near one edge. As it rises, the whole loaf tilts slightly. Our universe might have its own primordial tilt, a relic of its messy birth. Skeptics argue it could be a measurement error or an undiscovered local structure. But if dark flow is real, it rewrites the rules. Either our universe isn't as uniform as we thought, or we're feeling the gravitational breath of something from outside it. Future telescopes mapping galaxy motions in even finer detail might settle the debate. Until then, dark flow remains a ghostly fingerprint on the cosmos, hinting that whatever's out there is far stranger than we've dared to imagine. There's something unsettling about the cosmic microwave background, the afterglow of the Big Bang, that physicists don't like to talk about. It's called the axis of evil, and no, that's not a Hollywood disaster movie title. This spine-chilling nickname refers to a pattern in the oldest light in the universe that seems to align weirdly with our own solar system's plane. Imagine drawing a map of the cosmos's birth, only to discover it's subtly tilted toward your hometown. That's the level of cosmic coincidence we're dealing with, and it's either a clue to something profound or the universe playing a trick on us. The story starts with the Planck satellite, which mapped the CMB's temperature fluctuations with razor-sharp precision. These tiny hot and cold spots should be randomly scattered like static on an old TV. But when scientists analyzed the data, they found an eerie correlation. The largest-scale patterns align roughly with the ecliptic, the plane of Earth's orbit around the Sun. It's as if the universe's blueprint has a faint arrow pointing directly at us, which, according to the Copernican principle, shouldn't happen. We're not supposed to be special. The cosmos doesn't do center-stage placements. One camp argues this is just observational bias. Maybe dust in our solar system distorts the measurements, or perhaps the way we process the data introduces hidden artifacts. After all, seeing faces in clouds doesn't mean the sky is haunted, but others whisper a darker possibility. What if this alignment is real? Some theories suggest the axis of evil could be a scar from before the Big Bang, an imprint of an earlier universe that brushed against ours during a cosmic cycle. String theorists propose that our universe might be a four-dimensional brane that collided with another, leaving behind a preferred direction in space-time. The boldest idea, the alignment might hint that the universe isn't isotropic uniform in all directions but has a hidden structure, like a crystal with invisible seams. If true, it would upend Einstein's assumption that space looks the same no matter where you're standing. Future CMB experiments, like the proposed CMB S4 project, could settle the debate. But for now, the axis of evil lingers like a shadow in the data, taunting us with the possibility that our cosmic address isn't as random as we thought. And that's a problem physics can't ignore. Deep in the constellation Norma, something invisible is bending the path of galaxies like a cosmic puppeteer. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it's dragging the Milky Way and hundreds of thousands of other galaxies toward it at 14 million miles per hour. But here's the catch: when we point our telescopes in that direction, there's nothing big enough to explain the pull. No supercluster, no concentration of dark matter, just a faint smudge of galaxies that together shouldn't have this much sway. It's as if the universe has a hidden anchor and we're all caught in its tide. The mystery began in the 1970s when astronomers noticed something odd about the motion of nearby galaxies. Instead of drifting apart evenly with the universe's expansion, they were all streaming toward the same patch of sky like iron filings drawn to a magnet we couldn't see. At first, scientists assumed it was just a local overdensity, perhaps the Virgo supercluster exerting extra pull. But as observations improved, the numbers refused to add up. The Great Attractor's gravitational influence suggests a mass equivalent to tens of thousands of Milky Ways, yet visible matter accounts for less than 10% of that. One leading theory points to dark matter, the invisible scaffolding thought to weave through the cosmos. If there's an especially dense knot of it lurking behind the zone of avoidance, an area obscured by dust and stars from our own galaxy, that could explain the tug. But some calculations suggest even dark matter might not be enough. That's where wilder ideas creep in. Could the Great Attractor be a portal to another dimension where gravity leaks into our universe? String theory allows for such possibilities. Massive objects in higher dimensions might cast shadows of gravity we can't directly observe. Or perhaps it's not a single object at all, but a ripple in the fabric of spacetime itself. Inflationary models predict that quantum fluctuations during the Big Bang could have created primordial density waves, frozen into the universe like grooves in a record. These waves might funnel galaxies along invisible currents, giving the illusion of a central attractor. There's even a chance we're seeing the fingerprint of something older than our universe, a relic from a previous cosmic cycle, its gravity still echoing through the void. The intrigue deepened in 2005 when astronomers discovered the Shapley supercluster, an even more distant concentration of mass sitting behind the Great Attractor. Some argue Shapley's gravity might be the real culprit, with the attractor merely a waypoint. But others note the math still doesn't balance. Shapley's pull seems too far away to account for the full effect. Future radio telescopes peering through the zone of avoidance might finally unveil what's lurking there. Until then, the Great Attractor remains one of cosmology's most tantalizing blind spots, a reminder that even as we map the cosmos, the universe keeps its deepest secrets just out of sight. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic cycle of collapse and rebirth? This is the radical heart of the Big Bounce theory, a vision where the universe doesn't flame out into cold emptiness or rip itself apart. Instead, it contracts in a big crunch, rebounds, and explodes outward again in a new fiery dawn, over and over for eternity. Picture a cosmic accordion breathing in and out on scales so vast, a single inhale could last 1 trillion years. This idea appends the traditional Big Bang narrative, which starts with a singularity, a point of infinite density where physics breaks down. The Big Bounce sidesteps that problem entirely. Here, the universe never reaches true infinity. Instead, as it collapses under its own gravity, quantum effects at the tiniest scales kick in like a cosmic trampoline, pushing back against the crush. Think of it like squeezing a spring. Push hard enough and it resists, snapping back with stored energy. In this case, the spring is spacetime itself, and the snap is a new Big Bang. The key player in this drama, loop quantum gravity, a lesser-known rival to string theory. While string theory imagines tiny vibrating threads, loop quantum gravity proposes spacetime is woven from finite, interlocking loops. Think of a mesh fabric where each thread can't be divided further. This granular structure means gravity can't become infinite, no matter how dense the universe gets. As collapse nears its peak, these loops generate a repulsive force, turning the tide from contraction to expansion. It's a cosmic safety valve, preventing the universe from vanishing into a mathematical paradox. Evidence for this cyclical universe might already be hiding in plain sight. Some theorists argue that if a previous universe existed before ours, gravitational waves from its death throes could have imprinted faint swirls in the cosmic microwave background. Others hunt for anomalies in the distribution of galaxies, ghostly echoes of a pre-Big Bang structure. Even dark energy, the mysterious force accelerating our universe's expansion, fits oddly well into bounce models. Instead of a one-way ticket to emptiness, dark energy might be the universe gathering momentum for its next collapse. Critics argue we'll never prove a pre-Big Bang past, but the implications are staggering. If the Big Bounce is real, time has no true start or end, just an endless rhythm of creation and destruction. Stars, galaxies, even life itself would rise and fall in infinite variations across cycles. And somewhere in the distant future, when our universe finally exhausts its expansion and begins the long fall backward, the seeds of the next cosmic dawn will already be stirring in the quantum foam. What if the Big Bang wasn't an explosion at all, but a cosmic fender bender? That's the startling premise of the ekpyrotic universe theory, which swaps the traditional fireball beginning for something far more elegant, a collision between two branes, those mysterious higher dimensional membranes we've encountered before. Picture two sheets of paper floating in a dark room, drifting closer until they smack together. In that millionth of a second of impact, energy explodes outward, not from a single point but across an entire surface. That's how our universe might have been born, not from a singularity but from a crash in the 11th dimension. The beauty of this model is how it sidesteps the Big Bang's thorniest problem, the singularity. In standard cosmology, everything emerges from an infinitely dense, infinitely hot point where the laws of physics break down. It's like a math error in the core of reality. But in the ekpyrotic scenario, there's no infinity, just two branes, each carrying the remnants of a previous universe, colliding in a process that converts their kinetic energy into matter and radiation. Think of it like clapping your hands. The energy of motion becomes sound waves rippling through air. Here, the sound waves are the seeds of galaxies, and the air is the fabric of our three-dimensional brain. This solves another cosmic mystery: why the universe is so uniform. The microwave background shows temperature variations of just 1 part in 100,000, far too smooth for a random explosion. Inflation theory explains this by proposing space expanded faster than light, stretching irregularities flat. But the ekpyrotic model suggests another answer. If our universe was born from a glancing brane collision, the impact would have naturally smoothed everything out like rolling dough with an infinitely wide pin. The branes themselves act as cosmic sandpaper, erasing wrinkles as they scrape past each other over eons before finally making contact. The theory isn't just elegant, it's testable. Unlike some multiverse ideas, ekpyrosis leaves fingerprints. When branes collide, they don't just produce heat, they generate gravitational waves with a distinct pattern, different from those predicted by inflation. Future observatories like the Laser Interferometer Space Antenna could spot these ripples in spacetime, hunting for whispers from before time as we know it. Even more intriguing, this model hints that dark matter might be leftover debris from the previous brane universe particles stranded in our dimension when the cosmic sheets parted ways. Perhaps the most mind-bending implication is cyclical time. If branes can collide once, why not again? The ekpyrotic universe suggests an endless dance, branes drifting apart, drawn back together by hidden forces, crashing and rebounding in a cycle without beginning or end. Each collision resets the cosmic clock, wiping clean the past while seeding the future. So the next time you gaze at the night sky, consider this. The stars above might not be the first to burn in this cosmic theater, just the latest act in a show that's been running for eternity. What if everything you see, the stars, the laws of physics, even the neurons firing in your brain, isn't real in the way you think? Not in the solipsistic, maybe it's all a dream sense, but something far more concrete. Our universe could be an artificial simulation running on hardware built by some advanced civilization. This is the simulation hypothesis, and it's not just a plot twist from the Matrix. Philosophers, tech billionaires, and physicists have all treated it as a serious possibility. Nick Bostrom, the Oxford thinker who formalized the idea, laid it out as a trilemma, 3 unsettling options, at least one of which must be true. Either civilizations always go extinct before developing simulation technology, or they choose not to run ancestor simulations, or we're almost certainly living in one right now. Bostrom's argument hinges on scale. If a civilization could one day create simulations so detailed that simulated minds possess consciousness, think Westworld but with quantum fidelity, then the number of simulated beings would dwarf biological ones. The math is simple. For every real universe, there could be billions of simulations nested inside it. Statistically, the odds that we're in the original reality shrink to near zero. Elon Musk famously put it this way: the odds we're in base reality, 1 in billions. But this isn't just philosophical musing. Glitches in our universe's code might already be visible. Take quantum indeterminacy, the fact particles don't have definite states until observed. It's eerily like a video game rendering graphics only when a player looks at them to save processing power. Or consider mathematical constants like the fine structure constant, which seem arbitrarily fine-tuned for complexity. Could these be preset parameters chosen by programmers to see what emerges? Even the pixelation of spacetime at the Planck scale, the smallest meaningful unit of distance, hints at a possible resolution limit, like a cosmic version of pixels on a screen. Critics counter that the hypothesis is unfalsifiable. If the simulation is perfect, how could we ever detect it? But some scientists are actively hunting for anomalies. One team proposed checking whether the universe discretizes energy at ultra-high scales, a potential artifact of finite computing. Others suggest looking for rounding errors in physical constants over time, tiny drifts that might reveal the simulation's underlying numerical precision. And if our reality is a simulation, its creators might have left Easter eggs, mathematical patterns or quantum behaviors that serve as signatures of design. The most haunting implication: if we're in a simulation, our descendants might one day build their own nesting realities within realities, like Russian dolls. And somewhere up the chain, a being might be staring at a screen, watching this very moment play out as a historical curiosity, wondering if their own world is just another layer in the stack. Suddenly, the age-old question, "Why are we here?" takes on a whole new meaning. Imagine falling into a black hole, not the Hollywood version with spinning portals and flashing lights, but the real deal, where gravity warps space-time beyond recognition. Now stretch that thought further. What if our entire universe is the interior of a black hole in some larger parent cosmos? This is the black hole universe theory, a mind-bending twist on cosmology that turns the night sky into something even stranger: the glowing walls of a cosmic prison we can never see beyond. The idea isn't as far-fetched as it sounds. When a star collapses into a black hole, the equations of general relativity predict something bizarre. Inside the event horizon, space and time switch roles. What we perceive as the inevitable march of time toward the future becomes mathematically a direction in space, like a one-way corridor leading toward the singularity. For us, that singularity isn't a point of destruction but the Big Bang itself. Think of it like a cosmic Russian doll. Our universe's birth might have been the moment a black hole formed in another universe, sealing us off inside its gravitational tomb. This solves two of physics' greatest puzzles in one swoop. First, dark energy, the mysterious force accelerating the universe's expansion. If we're inside a black hole, the outward push could be the remnant energy of the parent star's collapse, still echoing through space-time like a gravitational aftershock. Second, the arrow of time, why we remember the past but not the future. In this model, time's one-way flow isn't fundamental. It's an artifact of our trapped perspective, like a river flowing downhill because that's the only direction gravity allows. The theory also explains why our universe seems so finely tuned for complexity. Black holes aren't random shredders, they're precision engines that compress matter into states of extreme order. The laws of physics we know, electromagnetism, the nuclear forces might just be the operating system of this cosmic computer, emergent properties of the way information gets scrambled at the singularity. Even the universe's uniformity makes sense. A black hole's interior would naturally homogenize like ingredients in a blender, erasing any traces of its parent universe. Critics argue we'll never peek beyond the event horizon to check, but clues might lurk closer to home. Some models predict that if our universe is a black hole, its expansion rate should correlate with the parent black hole's mass, a number we can estimate from the cosmic microwave background. Others suggest that quantum fluctuations in the early universe might carry fingerprints of the parent cosmos's physics, like shadows on a cave wall. And if this theory holds, the implications are dizzying. Every black hole in our universe could contain its own cosmos, bubbling with galaxies and life, forever hidden behind a veil of darkness. So the next time you gaze at the stars, consider this. You might not be looking out into space, but inward toward the crushing heart of a reality we'll never escape. And somewhere beyond that infinite night, another universe's scientists could be staring at their sky, wondering the same thing. Zoom in on a spiral galaxy, and you might notice its swirling arms look eerily similar to the patterns of a hurricane seen from space. Pull back further, and the cosmic web of galaxies resembles the branching veins of a leaf or the neural networks of a human brain. This isn't coincidence, it's the tantalizing hint of a fractal universe, where the same shapes repeat at every scale, from the tiniest quantum fluctuations to the vast superclusters that span billions of light years. The idea didn't start with astronomers, it came from a mathematician staring at coastlines. Benoit Mandelbrot, the father of fractal geometry, once asked a deceptively simple question: how long is the coast of Britain? The answer depends on your ruler's size. Measure with a yardstick, and you'll get one number. Use a grain of sand, and the length explodes as you trace every microscopic bump and crevice. The universe, Mandelbrot realized, might work the same way. Fractals aren't just pretty patterns, they're mathematical objects with infinite complexity. Take the Mandelbrot set. A single equation generates shapes that nest within themselves forever, revealing new layers no matter how far you zoom. Apply this to cosmology, and you get a radical vision. The universe isn't just filled with fractals. It is a self-repeating structure where clusters of galaxies organize into larger clusters, which themselves form part of even grander designs ad infinitum. Some models suggest this could explain the uneven distribution of matter we see. Instead of randomness, there's a hidden order, like a cosmic fingerprint pressed into the fabric of space. But here's the catch: to call the universe a true fractal, the pattern must hold at all scales. Observations so far show it works beautifully from galaxies up to superclusters, but beyond that, the data gets fuzzy. The cosmic microwave background, our baby picture of the universe, appears mostly smooth, with fluctuations too subtle to fit a perfect fractal model. Critics argue this smoothness is a death knell for the idea. If the universe were truly scale invariant, we'd see sharper contrasts in the early cosmos. Others counter that we're limited by our observational horizon. Just as a sailor on a vast ocean might mistake the Earth for flat, our telescopes might simply lack the reach to see the next level of cosmic repetition. The implications stagger the mind. If the fractal pattern holds, there's no true edge to the universe, just an endless recursion of structures, each a microcosm of the whole. Stars could orbit in galaxies that themselves orbit supermassive black holes, acting as atoms in some hypergalactic molecule. And if the cycle continues downward, even subatomic particles might contain entire universes, their quarks and leptons spinning like miniature galaxies. It's a hall of mirrors where every reflection holds another world. Yet perhaps the most poetic twist is how this blurs the line between math and reality. Mandelbrot once said, "Fractals are not just about geometry, they're a way to describe the rough, chaotic, and irregular patterns of nature." If he was right, then the universe isn't just described by math. It might be math, a living equation where every spiral, every cluster, is a stroke of some cosmic brush painting the same shape across the canvas of existence. The night sky, then, isn't just a scattering of lights, it's a single idea echoing across the void. What if time itself could crystallize, not just flowing forward like a river, but locking into repeating patterns like the facets of a diamond. This is the bizarre promise of time crystal structures that don't just exist in space, but pulse rhythmically in the fourth dimension, turning time into something more than a one-way street. The idea sounds like pure science fiction, but in 2016, Nobel laureate Frank Wilczek proposed it as a real possibility, and by 2017, labs had actually created these strange objects. Now, some physicists suspect they might hold the key to understanding the universe's deepest architecture. Time crystals defy everything we know about equilibrium. Normal crystals like snowflakes or salt are atoms arranged in repeating spatial patterns. They're stable, unchanging. But time crystals flip the script. Their atoms oscillate between states perpetually, like a clock that ticks forever without winding down. Picture a group of dancers spinning in perfect sync, never missing a beat even if the music stops. That's what happens inside a time crystal. They don't just resist entropy, they cheat it, creating order from chaos in a way that seems to bend the laws of thermodynamics. The secret lies in quantum entanglement. In a lab at Harvard, scientists used diamond imperfections, nitrogen atoms trapped in a carbon lattice, to build a primitive time crystal. When zapped with lasers, the entangled atoms began flipping their spins in a precise rhythm, locked in a dance that repeated like clockwork. No energy entered or left the system, yet the pattern persisted. It's as if the atoms found a loophole in physics, a way to keep moving without ever running down. Wilczek compares it to a perpetual motion machine, but one that doesn't violate energy laws. It just redirects them like a river finding a hidden channel. Now stretch this concept to cosmic scales. If tiny time crystals can exist in a lab, could the universe itself be a vast four-dimensional crystal with time as its repeating lattice? Some theories suggest that spacetime might have an underlying crystalline structure at the Planck scale, the smallest possible unit of measurement. Instead of being smooth and continuous, time would advance in discrete ticks like frames in a film. This could explain quantum weirdness, why particles seem to jump between states without intermediate steps. The universe wouldn't flow, it would vibrate, with every moment a snapshot in an infinite flipbook. Even stranger, a time crystal universe might solve the mystery of dark energy. If spacetime's structure naturally oscillates, those vibrations could push galaxies apart, mimicking an invisible force. And if time's flow is an emergent property, something that arises from deeper cyclical physics, it would rewrite our understanding of causality. Events wouldn't just happen, they'd resonate, echoing across dimensions like ripples in a pond. The wildest implication, time itself might be an illusion, a side effect of these grand cosmic vibrations. We perceive it as linear, past to present to future, but in a time crystal reality, all moments could exist simultaneously, stacked like layers in an onion. The future isn't written, it's crystallizing, and somewhere in the quantum foam, the universe might still be humming its first perfect note. The cosmos might not just look like a neural network, it could function like one. Picture the universe not as a cold, mechanical clockwork, but as a vast, self-organizing system where every galaxy, every atom, is a node in an incomprehensibly large cosmic brain. This isn't just poetic metaphor. Some physicists now argue that the universe's fundamental structure mirrors the way neurons connect and fire in our own minds, with quantum entanglement acting like synaptic links and gravity emerging from the collective learning of spacetime itself. Start with entanglement, that eerie quantum phenomenon where particles instantly influence each other across vast distances. In a brain, neurons communicate through electrochemical signals, forming networks that give rise to thought. Now imagine entangled particles as cosmic neurons, with their instantaneous connections weaving a web of relationships that underpins reality. The more entangled particles become, the more complex the cosmic thoughts, stars, galaxies, even life might emerge. Just as memories form through strengthened neural pathways, the universe's structure could solidify through quantum links that grow more robust over time. This idea dovetails with theories of emergent gravity, like Eric Verland's controversial hypothesis. Gravity, in this view, isn't a fundamental force but a side effect, a statistical mirage, like how temperature emerges from countless molecular collisions. In the neural network universe, gravity might arise from the way spacetime processes information, adjusting its connections like a brain rewiring itself. Think of it as cosmic deep learning. The universe tunes its own rules through experience, with black holes acting as dense clusters of knowledge where information gets compressed and reprocessed. Even the universe's expansion could fit this model. If spacetime is a neural net, its growth might resemble a brain forming new connections, not just stretching but evolving. Dark energy, then, could be the system's way of exploring new configurations, like a mind brainstorming possibilities. And just as neural networks develop hierarchies, simple patterns giving rise to complex abstractions, the cosmos might organize matter into galaxies, clusters, and superclusters, each layer encoding deeper levels of cosmic understanding. Critics dismiss this as speculative, but tantalizing hints abound. The similarity between galactic webs and neural structures is uncanny, down to the fractal branching patterns. Even the universe's information capacity aligns with theoretical limits for neural computation. Of course, this doesn't mean the universe is conscious, but it might operate by similar principles, with physical laws emerging from something akin to cosmic trial and error. If this theory holds, it blurs the line between physics and intelligence. The universe isn't just described by math, it might be math in motion, a self-optimizing algorithm iterating toward complexity. And somewhere in that vast network, our tiny planetary node is buzzing with activity, trying to decode the very system that gave it birth. Picture a universe so stretched and thin that galaxies dissolve into spectral ghosts, stars evaporate like morning mist, and the very atoms holding your body together are torn apart by an invisible force growing stronger every second. This isn't a nightmare, it's the phantom universe, one of cosmology's most chilling forecasts for how everything might end. At its heart lies dark energy, the mysterious force accelerating the universe's expansion. But what if it doesn't just keep pushing galaxies apart gently? What if it grows stronger over time, becoming a cosmic hurricane that rips reality itself to shreds? The doomsday scenario here is called the Big Rip, and its timeline reads like a horror script written by gravity. First, dark energy's grip tightens. Galaxies outside our local group vanish over the cosmic horizon, their light stretched into undetectable infrared whispers. Then gravity loses its footing. The Milky Way and Andromeda, destined to collide in a few billion years, never get the chance. The phantom force yanks them apart first. Stars are next. Around 60 million years before the end, dark energy overpowers even the nuclear bonds within them, reducing suns to clouds of scattered plasma. But the true horror comes in the final months. Planets are ripped from their orbits, then dismantled atom by atom. Minutes before the end, molecules disintegrate. In the last incomprehensible fraction of a second, spacetime itself fractures at the quantum level, shattering into a foam of disconnected fragments. No black holes, no heat death, just an infinite sea of unbound particles, each isolated in its own phantom realm. The math behind this hinges on something called the phantom energy equation of state. If dark energy's pressure-to-density ratio drops below -1, meaning it grows stronger as space expands, the universe becomes its own executioner. Some models even suggest this could happen within 22 billion years, a blink in cosmic terms. Yet there's a twist. A few theorists argue the Big Rip might not be the end. If spacetime shreds completely, it could reboot the cosmos like a computer crashing and rebooting. The resulting singularity might birth a new universe, one where dark energy's phantom grip becomes the next Big Bang. It's a grim irony. The force that destroys everything could also be the seed of its rebirth. Until then, the phantom universe remains a spectral warning, a reminder that even the void might not be forever. There's a mirror version of reality where time flows backward, matter is swapped for antimatter, and left becomes right. This isn't science fiction, it's a serious prediction of physics called CPT symmetry, and it might hold the key to one of the universe's greatest mysteries. The idea springs from one of the most fundamental principles in nature, that the laws of physics should stay the same if you flip charge, parity, and time all at once. Take an electron, flip its charge turning it into a positron, mirror its position swapping left for right, and reverse its motion through time, and it should behave exactly like the original electron. This symmetry is so ironclad, no experiment has ever broken it. But here's the twist: if the universe obeys CPT perfectly, there might be an entire anti-universe stretching backward from the Big Bang, filled with antimatter galaxies, stars, even life, all perfectly balanced against our own. Picture a cosmic hourglass. Our universe flows downward from the Big Bang as we know it, while its mirror image flows upward, a perfect reversal. In this anti-universe, particles we've never detected could be the dominant form of matter, obeying the same physics but inverted. Some theorists suggest these hidden particles might explain dark matter's gravitational grip without requiring new physics. Imagine a world where protons are negative and electrons positive, where time's arrow points toward a singular beginning we'd perceive as their end. The eerie part, we'd never see this mirror realm directly. Light from their stars wouldn't reach us. The two universes communicate only through gravity, their mutual pull shaping the web of galaxies we observe. This isn't just elegant math. Observations of cosmic inflation hint that the early universe was far more orderly than randomness would allow. A CPT-mirrored origin could explain that, like an inkblot folded perfectly in half, symmetry at birth would imprint balance on the cosmos. Even neutrinos, those ghostly particles that barely interact with matter, fit the puzzle. They're left-handed in our universe, spinning only one way. If the mirror universe has right-handed neutrinos, their combined existence could solve why matter outweighed antimatter after the Big Bang. The boldest idea. Dark matter might be the gravitational shadow of this anti-universe, its particles tugging on ours through dimensions we can't perceive. Experiments hunting for weakly interacting massive particles, WIMP, could actually be sensing echoes from the other side of time. And if CPT symmetry holds absolutely, then somewhere beyond the veil, another version of you is living this moment in reverse, their yesterday our tomorrow, their breath in our exhale, a cosmic dance of opposites, forever entwined yet forever out of reach. Dark energy might not be some mysterious force lurking in empty space. It could be an illusion, a cosmic sleight of hand born from the universe's information limits. This is the startling premise of holographic dark energy, a theory that stitches together two of physics' most radical ideas, the holographic principle and the accelerating expansion of the cosmos. Picture the universe as a giant hard drive. Just as your phone slows down when storage fills up, spacetime itself might be governed by how much information it can hold at its edges. The more the universe grows, the more its memory stretches thin, and that strain could manifest as the repulsive force we call dark energy. The math behind this is as elegant as it is strange. In the 1990s, physicists discovered a surprising link between entropy, a measure of disorder, and the boundaries of space. A black hole's maximum entropy, they found, doesn't scale with its volume but with its surface area. This hinted that reality might not be three-dimensional at its core, but two-dimensional information painted onto a distant horizon like a cosmic QR code. Fast forward to dark energy. If the universe has an information limit tied to its horizon, every new cubic meter of space that forms during expansion comes with a hidden tax and energy cost to encode its existence. That tax could be the dark energy pushing galaxies apart. Here's where it gets wild. The holographic principle suggests that the vacuum of space isn't truly empty. It's buzzing with quantum fluctuations, virtual particles popping in and out of existence. Normally, these fluctuations should generate far more energy than we observe, enough to tear atoms apart. But if information limits cap how much energy can arise in a given volume, it would neatly explain why dark energy is so faint yet pervasive. The universe isn't being pushed apart by some exotic substance, it's being shoved by the sheer cost of maintaining its own data storage. This theory also solves one of cosmology's biggest headaches, the cosmological constant problem. Quantum field theory predicts a vacuum energy density 120 orders of magnitude stronger than what we measure. That's like calculating the weight of a feather and getting the mass of a galaxy instead. But holographic dark energy bridges the gap by tethering vacuum energy to the universe's horizon size, a cosmic checks and balances system where information limits keep energy densities in line. Observational clues are starting to stack up. Measurements of the universe's expansion rate align eerily well with holographic predictions, especially when factoring in the Hubble tension, the discrepancy between local and distant measurements of cosmic growth. Some models even suggest that if dark energy is holographic, its strength should evolve in lockstep with the universe's horizon, offering a testable fingerprint. Future galaxy surveys and gravitational wave detectors could spot this subtle shift, turning a radical theory into hard science. The implications rewrite our place in the cosmos. If holographic dark energy is real, the universe isn't just expanding, it's rendering itself into existence, pixel by pixel, with every new region of space demanding a slice of some fundamental cosmic bandwidth. And that means the fate of everything, whether galaxies drift apart forever or collapse in a big crunch, might hinge not on gravity or dark matter, but on something far more primal, the universe's ability to remember itself. What if spacetime isn't smooth and flowing like a river, but more like a pile of sand, countless tiny grains stacked together, each representing a single moment of cause and effect? This is the radical vision of the causal set universe, where reality isn't a continuous fabric but a vast network of discrete atoms of causality. Forget the infinite smoothness of Einstein's spacetime. Here, the universe operates like a cosmic flipbook, with each frame linked to the next in an unbreakable chain of events. The idea springs from a simple but profound problem: singularities. Black holes and the Big Bang both collapse into points of infinite density where the laws of physics break down. But infinities are almost always a sign that our theories are incomplete. Causal set theory offers an escape hatch. If spacetime is fundamentally granular, a collection of finite, indivisible moments, then there's no such thing as true infinity. No infinitely small points, no infinitely dense singularities. Just a universe built from tiny, irreducible time grains, each connected to others in a strict sequence of cause and effect. Picture a cosmic domino rally where each domino represents an event, and the entire chain forms the history of reality. This isn't just philosophical wordplay. The math behind causal sets reveals something startling. You don't need smooth spacetime to get gravity. Einstein's equations emerge naturally when you take this network of causal links and zoom out, just like a pixelated image looks smooth from a distance. And because the theory treats time and space as secondary, born from the relationships between events, it sidesteps the nightmare of quantum gravity. No more struggling to reconcile general relativity's smooth spacetime with quantum mechanics' discrete jumps. Here, discreteness is baked into the foundation. One of the most compelling predictions of causal set theory is a natural speed limit to change. Since each grain of spacetime can only influence a finite number of others, there's a built-in cap on how quickly information can propagate. This could explain why nothing travels faster than light without invoking arbitrary rules. It's just how the cosmic dominoes fall. Even more intriguing, the theory suggests spacetime might fluctuate at microscopic scales, with tiny causally disconnected regions blinking in and out of existence like quantum foam. Critics argue that causal sets are too abstract, lacking experimental hooks, but supporters point to subtle signatures. If spacetime is granular, high-energy cosmic rays might scatter in unexpected ways, revealing the universe's underlying graininess. Others hunt for anomalies in the cosmic microwave background, hints that the Big Bang wasn't a singularity, but a rapid cascade of causal events. If proven, this would rewrite our origin story. The Big Bang wasn't a single explosion, it was the first domino in an unbroken chain stretching to today. The implications ripple outward. A causal set universe doesn't just eliminate singularities, it redefines time itself. There's no flowing river of moments, just a vast, unchangeable network of relationships. The now you feel is an illusion, a spotlight moving through the causal web. And somewhere in that web, every possible past and future already exists, frozen in the cosmic lattice like frames in a film strip. The universe isn't becoming, it simply is, a masterpiece of cause and effect written in atoms of spacetime. What if the universe isn't just governed by the laws of physics, but by something far more primal, information itself? Imagine spacetime not as a stage where particles move, but as a vast, self-repairing quantum code, meticulously designed to prevent cosmic data from decaying into noise. This is the wild promise of the universe as a quantum error-correcting code, an idea that blurs the line between physics and computer science. At its core is a startling realization. The way particles entangle and interact mirrors the very algorithms tech giants use to protect your data from corruption. The cosmos, in this view, might be the ultimate supercomputer, with spacetime acting as its fault-tolerant hard drive. The roots of this theory stretch back to a paradox that nearly tore physics apart: the black hole firewall problem. When quantum mechanics clashes with general relativity at a black hole's edge, calculations suggest an invisible wall of searing energy should vaporize anything falling in. But that contradicts Einstein's insistence that free-falling observers should feel nothing unusual. The solution: think of a black hole's event horizon not as a destructive boundary, but as a cryptographic firewall. Just as error-correcting codes in your phone fix flipped bits caused by cosmic rays, spacetime might employ quantum entanglement to repair disturbances before they erase information. The firewall isn't physical, it's a computational failsafe, ensuring data isn't lost but scrambled and preserved. This ties into one of theoretical physics' most profound discoveries, the anti-de Sitter/conformal field theory, AD-S/CFT duality. In simple terms, it suggests that a higher dimensional universe with gravity like ours can be perfectly described by a lower dimensional quantum system without gravity, a hologram in the truest sense. Now pair that with quantum error correction. The holographic screen at the universe's edge isn't just projecting reality, it's actively debugging it, using entanglement to stitch spacetime into a coherent whole. Picture a cosmic game of telephone where messages passed between particles don't degrade over distance because the universe's code constantly checks for errors. The implications rewrite how we see reality. Black holes aren't information destroyers but vaults, encoding data in their event horizons like cosmic Blu-ray discs. The Big Bang's uniformity, not luck, but the result of a universe-wide error correction protocol smoothing out glitches. Even dark energy could be a side effect, a kind of computational overhead, as the cosmos scales up its storage capacity. And if this theory holds, it hints at something staggering. The laws we call physics might just be emergent properties of a deeper, informational architecture, like the rules of chess emerging from the logic of its code. Here's where it gets even stranger. If spacetime is a quantum code, its bits might be woven from entanglement itself. Every particle interaction, every gravitational tug, could be part of a vast cosmic checksum, ensuring consistency across the universe. Fail one check and the system auto-corrects, perhaps explaining why quantum particles seem to choose states only when observed. The universe isn't just computing, it's proofreading itself in real time. Critics argue this leans too heavily on metaphor, but the math is concrete. Error-correcting codes share uncanny symmetries with quantum field theories, and recent experiments with quantum computers show similar self-repairing behaviors in microcosm. Future tests could look for telltale signatures in the cosmic microwave background, anomalies that resemble corrected fluctuations. And if the theory's right, it means every star, every atom, is part of a grand computational tapestry, humming with the quiet precision of a universe that refuses to forget. Think of a swarm of fireflies blinking in perfect synchrony on a summer night, each tiny light acting independently, yet together creating a pattern that seems orchestrated by some unseen hand. Now imagine spacetime working the same way, not as a fundamental backdrop to the universe, but as an illusion emerging from countless quantum connections humming beneath the surface. This is the radical idea of the emergent universe, where the stage itself, the very fabric of space and time, isn't primary, but something that crystallizes from deeper, more primitive building blocks, quantum entanglement. The concept turns classical physics on its head. We're used to thinking of spacetime as the canvas on which reality unfolds, the unchanging grid where particles move and forces act. But just as temperature isn't a tangible thing but a collective property of atomic motion, spacetime might be a secondary effect, a kind of cosmic mirage. Picture the surface of a lake, smooth and continuous from afar, but up close, it's just countless water molecules jostling. Similarly, the smooth geometry Einstein described could be the large-scale ripple of microscopic quantum bonds. This idea gained traction with a breakthrough in the 1990s. Physicists discovered that black holes obey a strange accounting rule. Their maximum entropy, a measure of disorder, scales with their surface area, not their volume. It's like storing an entire library's worth of books on its front door rather than filling the shelves inside. This hinted that the information defining a black hole's contents might live on its boundary, with spacetime in the interior emerging like a hologram from that data. Extend this to the whole universe and you get a staggering possibility. Our 3D reality might be a projection from a 2D network of entangled quantum bits at the cosmic edge. Entanglement is the glue here. When particles become entangled, their properties link instantaneously across distances, defying classical notions of locality. Now imagine this happening on a cosmic scale. Every atom, every photon could be entwined in a vast web of connections, and from those threads, the illusion of continuous space weaves itself. It's like watching a movie. The motion feels fluid, but it's really just individual frames flashing by too fast to see. Spacetime might be the film our brains pass, while the universe's true frame rate operates at the Planck scale, a realm where quantum flickers stitch the fabric of reality together. Support comes from an unexpected place: quantum error correction. Tech companies use error-correcting codes to protect data from noise, spreading information across many bits so glitches can be detected and fixed. Remarkably, the equations governing spacetime's geometry mirror these codes. Black holes, for instance, might not destroy information but scramble and preserve it, like a cosmic hard drive running a self-repair algorithm. If spacetime is built from such protocols, it would explain why the universe resists paradoxes. It's literally debugging itself in real time. Critics argue this replaces one mystery with another. If spacetime emerges, what does it emerge from? Some theories point to quantum gravity, where the universe begins as a formless network of nodes like a blank circuit board. As these nodes entangle, they generate geometric structure like iron filings aligning into magnetic field lines. Others suggest time itself emerges from quantum interactions, with causality arising from the sequence of entangled events. There's even a wild possibility that dark matter and dark energy are side effects, artifacts of the universe's underlying code, struggling to render smooth spacetime at cosmic scales. The implications are profound. If spacetime isn't fundamental, singularities, those infinite densities in black holes and the Big Bang, might just be places where the quantum hardware overheats, so to speak. No more breakdown of physics, just a need for better debug tools. It also reshapes how we think about gravity. Einstein saw it as spacetime's curvature, but in an emergent universe, gravity could be more like thermodynamics, a statistical effect of deeper quantum mechanics, the way pressure emerges from countless molecular collisions. Experiments are catching up. Quantum simulators can now recreate microscopic models of emergent spacetime in labs, observing how entanglement generates geometry. Meanwhile, astronomers hunt for anomalies in distant quasars or cosmic rays that might reveal spacetime's pixelation. And if the theory holds, it means every step you take, every star you see, is part of a grand computation, a universe that isn't just described by math, but one that is math in motion, tirelessly knitting itself into existence one quantum thread at a time. What if the universe didn't need a creator or even a reason to exist? What if it simply bubbled into being from absolute nothingness, no divine spark, no pre-existing matter, just the raw, roiling chaos of quantum uncertainty? This is the provocative heart of A Universe from Nothing, a theory championed by physicist Lawrence Krauss that turns the cosmic origin story into something stranger than fiction. The key lies in the bizarre behavior of the quantum vacuum, a realm where nothing doesn't mean emptiness but a seething ocean of potential. Picture the vacuum of space. Far from being a static void, it's a carnival of virtual particles, electrons and positrons, quarks and antiquarks, constantly popping in and out of existence like fireflies in a midnight field. These quantum fluctuations borrow energy from nowhere, existing fleetingly before vanishing back into the void. Normally, they cancel out instantly, leaving no trace. But under the right conditions, Krauss argues, these fluctuations could stretch and freeze, inflating into an entire universe. It's like blowing a soap bubble so vast it becomes its own cosmos, with the bubble's skin encoding the laws of physics for everything inside. The math behind this is both elegant and unsettling. Quantum field theory shows that even in a perfect vacuum, a state with zero particles and zero classical energy, there's always a residual buzz, a kind of baseline agitation called zero-point energy. Combine this with general relativity, and spacetime itself becomes unstable, prone to sudden phase transitions. In this view, the Big Bang wasn't a singular event, but a quantum hiccup, a fluctuation that got out of hand. And if it happened once, it could happen endlessly, with universes budding off invisible dimensions like droplets condensing on cold glass. But here's the rub. Is this nothing really nothing? Critics like philosopher David Albert argue that Krauss's quantum vacuum is still a something, a rich, structured arena governed by precise physical laws. True nothingness, Albert insists, wouldn't even have the potential for fluctuation. It would be the absence of space, time, and quantum fields altogether. Think of it like a chessboard. You might start a game with no pieces, but the board and rules still exist. Krauss's nothing is the board. Albert wants to know where the board came from. Krauss counters that even the laws of physics might emerge spontaneously, like traffic patterns in a bustling city. In certain string theory models, the universe's rules aren't absolute, but frozen accidents, random symmetries that locked in during cosmic inflation. Imagine shaking a kaleidoscope. Every twist creates a new pattern, but only some are stable enough to persist. Our universe's physics could be one such pattern, with others playing out in distant bubbles. The implications stretch beyond academia. If universes can arise from quantum nothingness, then ours might be one of countless cosmic experiments, each with different constants, dimensions, even logics. Some might collapse instantly, others could harbor life and dark energy. The force accelerating our expansion might be the leftover tension from our universe's birth, like the shudder of a soap bubble detaching from its wand. Experiments can't yet probe the pre-Big Bang quantum foam, but clues might lurk in gravitational waves or the cosmic microwave background. If we find signatures of colliding bubble universes or anomalies in the sky's uniformity, it could bolster the case for spontaneous creation. Until then, the theory remains a dazzling thought experiment, one that challenges not just how the universe began, but what beginning even means. After all, if time itself emerged with the Big Bang, then asking what came before might be like asking what's north of the North Pole. The answer could be simpler and stranger than we've dared to imagine. Imagine waking up one day, your memories intact, the world around you perfectly coherent, only to realize you're a fleeting accident, a momentary spark of awareness flickering into existence from pure chaos. No past, no future, just a solitary mind hallucinating the entire universe around it. This is the chilling premise of the Boltzmann brane, a thought experiment that turns cosmology into a psychological thriller. Named after the 19th century physicist Ludwig Boltzmann, who grappled with entropy and the nature of randomness, the idea suggests that in an infinite, chaotic cosmos, self-aware entities could spontaneously assemble by sheer chance, complete with fake memories and sensory input. It's not just a curiosity, it's a direct challenge to how we understand reality, consciousness, and even the anthropic principle. To grasp why this isn't just philosophical hand-waving, consider entropy, the measure of disorder in the universe. Boltzmann realized that while entropy tends to increase over time, statistical fluctuations can create pockets of order like eddies in a rushing river. Most fluctuations are small, a gust of wind arranging leaves into a pattern or molecules clustering briefly in a gas, but given enough time and an infinite universe, even the most improbable events become inevitable. A fully formed, self-aware brain, complete with fabricated experiences, is just an extreme version of those fluctuations. The odds are astronomically low, but in an eternal cosmos, it's not just possible, it's statistically guaranteed. This leads to a paradox that keeps cosmologists up at night. If Boltzmann branes are more probable than entire, ordered universes, since a single brane requires far fewer particles to align randomly than a whole cosmos, why aren't we one of them? The anthropic principle, the idea that our observations are biased by the fact we exist to make them, seems insufficient here. After all, a Boltzmann brane would also feel convinced of its own reality, memories of childhood, even the laws of physics. The coffee cup in your hand, the screen you're reading this on, all could be a hallucination conjured by a disembodied brain that formed seconds ago, destined to dissolve back into chaos moments later. Some theories try to sidestep this horror. Eternal inflation, for example, suggests that while Boltzmann branes could form in the void between bubble universes, the sheer volume of space, INSIDE, Chinese letter, universes like ours makes real, stable observers vastly more common. Others argue that quantum gravity or the holographic principle might impose limits on how long a fluctuation can persist, preventing Boltzmann branes from lasting long enough to think. But the problem refuses to die. If the universe truly tends toward disorder over infinite time, then conscious observers like us should be vanishingly rare compared to these solitary, self-deceiving minds. The implications ripple far beyond metaphysics. If Boltzmann branes dominate the cosmic statistics, our scientific reasoning itself becomes suspect. Every experiment, every observation could be a figment of a transient mind's imagination. The laws of physics, just a convincing fiction. This isn't solipsism, it's worse, because even the solipsist assumes their own continuity. A Boltzmann brane has no history, no future, no external reality to anchor it. It's a universe's worth of illusion crammed into a single, doomed thought. Yet there's a strange beauty here, too. The Boltzmann brane forces us to confront the fragility of our assumptions. Why do we trust memory or logic or the consistency of nature because they've held so far? That's exactly what a Boltzmann brane would say. In the end, the thought experiment isn't just about brains in voids, it's a mirror held up to the limits of human knowledge. The cosmos might be vast, ancient, and ordered, or it might be a statistical ghost flickering in and out of existence. And the only thing we can truly know is that, for this moment at least, something is thinking these thoughts, whether it's a brain, a universe, or something beyond both. What if the universe isn't just expanding? It's stretching like the throat of a cosmic monster, a tunnel threaded between two unfathomable gulfs. This is the spine-tingling premise of the wormhole universe theory, where our entire cosmos isn't a lone bubble floating in the void, but the interior of a gargantuan wormhole, its exits anchored to black holes in some higher dimensional multiverse. Picture a soap bubble stretched between two rings, its shimmering surface hiding a hidden passage only here. The bubble is spacetime itself, and the rings are black holes older than time. The math behind this is less sci-fi than it sounds. Einstein's equations allow for wormholes bridges connecting distant points in space, though they typically require exotic matter to stay open. But in the 1990s, physicists like Leonard Susskind and Juan Maldacena realized something astonishing. Black holes might naturally form wormhole links through quantum entanglement. Imagine two black holes born from the same star collapse, their fates intertwined like quantum twins. Information falling into one could theoretically emerge from the other, not because it traveled through space, but because the holes share a hidden corridor, an Einstein-Rosen bridge aka a wormhole. Now scale that up. If two black holes in a parent universe became entangled, their interiors could inflate into an entire new cosmos with us living inside the tunnel. This solves cosmic riddles in one swoop. First, dark matter, the invisible glue holding galaxies together. If our universe is a wormhole, its walls could be lined with gravitational residue from the parent black holes, warping space in ways that mimic unseen mass. Like echoes bouncing down a pipe, these phantom forces might tug on stars without any particles to account for them. Even the universe's expansion fits neatly. Wormholes aren't static, their throats can stretch or contract. If ours is still adjusting to some primordial tension, that could manifest as dark energy's relentless push. The wildest implication, if this theory holds, black holes in our universe might themselves be budding wormholes, each birthing a new cosmos inside. We could be nested inside a black hole that's nested inside another, ad infinitum, a fractal chain of cosmic matryoshka dolls. And somewhere beyond the event horizons that birthed us, other universes might be thriving, their physics utterly alien, their skies lit by stars we can't begin to imagine. Critics argue wormhole universes are untestable, but subtle clues might lurk in gravity waves. When black holes collide, they ripple spacetime with a characteristic chirp. If our universe is a wormhole, those ripples could carry faint harmonics echoes of the larger structure we're embedded in. Others suggest hunting for anomalies in the cosmic microwave background, where a wormhole's geometry might leave faint concentric scars like rings in a bathtub. The most haunting thought, if we're inside a wormhole, there's no exit. The parent universes are forever beyond our horizon, their black hole mouths receding faster than light can chase. We're travelers in an eternal tunnel, riding the expansion of a universe that's itself just a stitch in the fabric of something infinitely stranger. So the next time you gaze at the night sky, remember, those stars might not be distant suns, but the glowing walls of a passage we'll never see the end of. Take the fabric of spacetime, the smooth, continuous stage Einstein described, and shatter it into a billion fragments. Not randomly, but with exquisite precision, like a master jeweler arranging diamonds into an invisible lattice. This is the vision of the universe as a quantum graph, where reality isn't woven from threads, but built from nodes and connections, a cosmic neural network humming beneath the surface of perception. Forget the idea of space as an empty container. Here, distance itself emerges from how many links separate 2 points in the web, and time, just another dimension in the graph, with causality acting like an algorithm updating the network state. The theory springs from a collision between two titans of physics, Einstein's general relativity, which paints gravity as the curvature of spacetime, and quantum mechanics, where particles hop between discrete states. Normally, these frameworks clash violently. Relativity loves smooth curves, quantum demands sharp jumps, but in a quantum graph universe, both find common ground. Picture a city subway map. The station's nodes represent discrete chunks of spacetime, while the routes between them edges encode gravitational and quantum relationships. A particle moving from Earth to Mars isn't traversing empty space. It's hopping nodes along optimized paths like a commuter switching trains. This isn't just metaphor. The math behind quantum gravity, yes, that's the actual term, reveals something astonishing. At high energies early in the universe, the graph might have been completely disordered, like a bowl of spaghetti with no structure. But as the cosmos cooled, connections froze into patterns that gave rise to the dimensions we know. Think of water crystallizing into ice. Molecules suddenly align, creating rigid axes where before there was only chaos. In this model, the 3 dimensions of space and 1 of time aren't fundamental, they're emergent properties, the statistical bias of how the graph's links stabilized. The implications rewrite cosmic history. The Big Bang wasn't an explosion in spacetime, but the moment the quantum graph underwent a phase transition, snapping from disorder to structured connectivity. Dark matter could be remnants of disconnected nodes, ghostly stations on the subway map with no trains running. Even black holes take on new meaning. Instead of singularities, they're regions where the graph's connectivity frays, like a torn mesh fabric with edges leading nowhere. Experimental clues might already exist. If spacetime has a granular structure, ultra-high-energy cosmic rays should behave oddly, like marbles rolling over a bumpy surface. Some theories predict these particles would travel slightly slower than light, their energy leaking into the graph's hidden dimensions. Intriguingly, the Pierre Auger Observatory has spotted cosmic rays with unexpected breaking patterns, though the data isn't conclusive yet. Another hunt involves gravitational waves. Just as seismic waves reveal Earth's layers, spacetime ripples from black hole mergers might carry harmonics hinting at the underlying graph's architecture. But the grandest idea lies in unification. Quantum gravity doesn't just reconcile relativity and quantum mechanics, it suggests they're 2 views of the same underlying code. Gravity emerges from the graph's overall connectivity, like the internet structure shaping how information flows. Quantum behavior, meanwhile, stems from local node interactions, like individual routers processing data packets. Even entanglement finds a natural home. Particles remain linked because their nodes share deep connections in the graph, regardless of apparent distance. The theory isn't without skeptics. Some argue it replaces one mystery with another. What determines the graph's rules? Others question whether it's testable enough to be science, not philosophy. But supporters counter that all fundamental theories start as math seeking reality. Once, atoms were just a useful idea, now we photograph them. If quantum gravity holds, we might one day glimpse the universe's scaffolding not through a telescope, but by decoding the subtle whispers of particles navigating the ultimate network. And that's the profound shift this idea demands. We're used to thinking of space as a void, an emptiness waiting to be filled. But a quantum graph universe suggests there is no emptiness, only relationships, vibrating connections humming the cosmos into being. The night sky isn't a vast nothingness dotted with stars. It's a dynamic web of meaning where every photon, every atom is a note in a grand symphony of structure. The universe doesn't exist in space. A space exists because the universe is. What if consciousness isn't something the universe has, but something the universe is? Not just a fluke of biology in human skulls, but a fundamental property of reality itself, like gravity or electromagnetism, woven into the fabric of existence from the Big Bang onward. This is the radical premise of panpsychism, an ancient idea that's staging a comeback in modern physics. Forget the notion of inert, dead matter rattling around in empty space. Here, even electrons might harbor whispers of experience, and galaxies could think vast, slow thoughts beyond human comprehension. The theory doesn't claim rocks are introspective or atoms ponder their choices. Instead, it suggests that consciousness isn't an on/off switch, but a spectrum from the dim flicker of a quark's experience to the roaring symphony of a human mind. Think of it like temperature. A single atom has kinetic energy, but we wouldn't call it hot. Only when trillions jostle together does heat emerge. Similarly, panpsychists argue, simple forms of awareness could combine into richer ones, like drops merging into a river. Integrated information theory, IIT, developed by neuroscientist Giulio Tononi, gives this idea mathematical teeth. IIT proposes that consciousness arises from the way information interacts within a system. The more integrated and complex those interactions, the richer the experience. Your brain's billions of neurons firing in precise synchrony generate your subjective awareness, but the math doesn't stop at brains. Apply IIT to the cosmic web, where galaxies are nodes entangled by gravity, and suddenly the universe itself could qualify as a conscious entity. Picture the Milky Way not just as stars and dust, but as a single thought in a mind larger than time. Critics scoff, how could a star field experience anything without neurons or senses? But panpsychists counter with a puzzle of their own. How does non-conscious matter? Particles blindly obeying physics suddenly spark into subjective feeling. This hard problem of consciousness, coined by philosopher David Chalmers, remains science's greatest blind spot. Panpsychism sidesteps it by removing the magic leap. If consciousness was always there, just rearranging itself into ever more complex forms, the problem melts away. The implications are staggering. If the cosmos has an interior life, even if utterly alien to our own, then black holes might not just warp space, they could be cosmic synapses, processing information in ways we can't fathom. Dark matter, invisible yet everywhere, might be the universe's silent partner in experience. Even quantum superposition, where particles exist in multiple states until observed, takes on new meaning. What if collapse isn't caused by human observation, but by the universe's own awareness interacting with itself? Some theorists go further. If consciousness is fundamental, then the laws of physics might not be arbitrary rules, but habits of a universe learning to know itself. The fine-tuning of constants for life, not luck but a bias toward complexity, a cosmos inclined to wake up. And if time is an illusion, as some quantum gravity models suggest, then all moments of awareness, from the first hydrogen atom's flutter to the last black hole's evaporation, might exist simultaneously in eternal now. Skeptics demand evidence. How do you test whether a star is aware? Panpsychists point to anomalies. Why does consciousness correlate so precisely with integrated information in brains? Why do some quantum systems seem to choose states in ways that defy classical probability? Future experiments might look for consciousness like behaviors in unexpected places, self-organizing systems, plasma filaments, even the large-scale structure of spacetime itself. But the deepest lesson might be philosophical. If panpsychism holds, we're not just in the universe, we're of it, fragments of a cosmic mind dreaming itself into existence. Every thought you've ever had, every moment of joy or sorrow, might be the universe reflecting on itself through you. And when you gaze at the night sky, you're not just a speck looking out, you're the cosmos looking back. Black holes devour everything: light, matter, even time itself. But what if their opposites exist, cosmic fountains spraying reality outward instead of swallowing it whole? Enter the white hole, one of general relativity's most tantalizing what-ifs. While black holes trap anything crossing their event horizons, white holes are theorized to be exits, regions of spacetime where nothing can enter, only erupt. Picture a black hole in Rewind. Instead of a crushing singularity sucking everything in, a white hole would have a singularity spewing energy, light, and matter in an unstoppable geyser. The equations allow it. Einstein's field recipes don't care which way time flows. Yet no white hole has ever been observed. That is, unless you consider the ultimate cosmic anomaly, the Big Bang itself. The similarities are eerie. Both white holes and the Big Bang represent singularities, points where density and curvature become infinite, and physics as we know it breaks down. But while black holes collapse matter into oblivion, white holes and the Big Bang explode it into existence. Some theorists suggest this isn't coincidence. Perhaps our universe didn't emerge from nothingness, but from the white hole eruption of a parent cosmos. Imagine a supermassive black hole in another universe collapsing, only to rebound as a white hole in ours, a cosmic Russian doll where every death spawns a new beginning. The math even hints at this. Certain solutions to quantum gravity equations show black holes could tunnel into white holes via quantum effects, like a straw poking through the fabric of spacetime and opening a new end. Here's where it gets wild. If the Big Bang was a white hole event, it would explain some of cosmology's deepest puzzles. The universe's staggering uniformity. The way the cosmic microwave background looks identical in opposite directions makes perfect sense if everything we see erupted from a single, ultra-coherent source. No need for inflations faster than light stretching. The white hole's singularity would have naturally smoothed everything before the eruption, like paint mixed in a can before the lid blows. Even dark energy fits neatly. White holes aren't static, their outbursts accelerate as they expel their contents. Sound familiar? It's exactly what we observe with the universe's expansion speeding up. But why can't we find white holes in space today? One possibility is they're ephemeral, flashing into existence only briefly before collapsing into black holes or dispersing. Another is that they're hiding in plain sight. Some models propose gamma-ray bursts, those incomprehensibly energetic flashes in distant galaxies. Could be white holes blinking into existence and vanishing just as fast. Others suggest quasars, the luminous hearts of young galaxies, might be powered by white hole-like dynamics, their colossal energy output matching theoretical predictions. The most radical idea: white holes might not just be relics of the past but gateways to the future. If black holes can transition into white holes over astronomical timescales, as quantum gravity models suggest, then every black hole we see might one day become a universe of its own. Our cosmos could be riding the shockwave of such a transformation right now. The aftermath of some long-dead civilization's collapsed star reborn as everything we know. It's a humbling thought. The night sky's blackest voids might not be tombs but cradles, and our entire existence could be the echo of another universe's end. 2,500 years ago, Pythagoras stood in a Greek courtyard, staring at the way stones chimed when struck, and declared the universe was made of numbers. Today, some of the brightest minds in physics are whispering he might have been onto something far stranger than he imagined. What if the cosmos isn't just described by mathematics? What if it is mathematics? Not equations scribbled on some cosmic chalkboard, but math incarnate, a single, self-unfolding equation where every star, every quark, every fleeting thought is just a term in a computation too vast to comprehend. This is the ultimate razor-cut ontology, reality as a mathematical singularity, a solitary idea dreaming itself into existence. Max Tegmark, the MIT physicist who championed this mathematical universe hypothesis, takes it further than Pythagoras ever dared. In his vision, our cosmos isn't one of many possible universes, it's one of many possible mathematical structures. Imagine a library where every book isn't a story about a world, but is that world, its pages woven from pure logic. A universe where gravity follows the inverse cube law instead of inverse square. That's just another volume, a realm with 11 dimensions and no time. Shelf 37, collecting dust. Our physics, then, isn't the foundation of reality. It's the local dialect of a deeper, number-driven truth. The elegance is dizzying. No more fretting about why the speed of light is 299 million meters per second, or why electrons have the charge they do. These aren't arbitrary constants, they're inevitable consequences of the mathematical structure we happen to inhabit. Even consciousness could be a computational pattern, a subroutine in the cosmic code. Tegmark's Level 4 Multiverse takes this to its logical extreme. Every consistent mathematical structure exists as a physical reality somewhere in the ensemble. The Mandelbrot set isn't just a pretty fractal, it's a universe unto itself, humming with alien complexity. Critics pounce, if the universe is math, where's the substance? Why does 2 plus 2 feel like something when neurons fire in a brain, but not when rocks tumble down a hill? Tegmark's rebuttal is slyly simple. The feeling is the math. Your experience of reading these words, the warmth of sunlight, the ache of nostalgia, they're all patterns in the data. The universe doesn't compute a brain and then add consciousness. The computation is the experience, like a video game engine that doesn't render graphics but is the graphics. The most haunting evidence might lie in the unreasonable effectiveness of mathematics. When Dirac wrote down an equation in 1928, it predicted antimatter before anyone had seen it. When Einstein molded spacetime with tensors, black holes fell out of the symbols like ripe fruit. Math doesn't just model reality, it often races ahead of it as if we're decoding a pre-written script. Tegmark argues this isn't coincidence, it's redundancy. We're not discovering laws, we're translating the universe's native tongue. So where does that leave us? In a cosmos stripped of metaphor, where the line between abstract and concrete dissolves, the Big Bang wasn't an explosion of matter, it was the first term in a cosmic proof. Dark energy, a side effect of the equation balancing itself, and you, reading this, a fleeting symmetry in the solution, a brushstroke in mathematics' self-portrait. Pythagoras heard the music of the spheres. Tegmark suggests we are the music notes in a composition so vast it writes itself into being. The equations don't describe the universe. They are the universe, and we're the part that's learned to read them. From holographic projections to cosmic brains, from universes birthed inside black holes to reality itself as a self-solving equation, we've ventured through 30 theories that don't just bend the rules of physics, they shatter them entirely. Each one starts with a simple "what if?" and spirals into realms where time loops like a ribbon, where consciousness might be the universe's operating system, and where the Big Bang could be just one note in an endless symphony of cosmic rebounds. These aren't just thought experiments, they're the bleeding edge of human curiosity, where mathematicians, physicists, and philosophers collide to redraw the map of existence. Take the holographic principle. What feels like a three-dimensional reality might be a two-dimensional code painted on the edge of space. Or the Boltzmann brane paradox, where your very thoughts could be a random fluctuation in an infinite void. And who could forget the phantom universe, where dark energy turns predator, tearing apart atoms in a final, crushing rip? These ideas don't just challenge our understanding, they demand we rethink what understanding even means. Science at this frontier isn't about finding answers, it's about learning to ask better questions. But here's the real magic: these theories aren't fantasy. They're grounded in equations, in observations, in the stubborn quirks of quantum particles and the cryptic whispers of the cosmic microwave background. When black holes behave like error-correcting computers, or when the universe's expansion hints at hidden dimensions, it's not just imagination, it's the cosmos dropping hints, inviting us to dig deeper. So now it's your turn. Which of these theories rewired your brain? Was it the chilling elegance of the mathematical universe or the cosmic déjà vu of the Big Bounce? Drop your favorite in the comments below. We're all just stardust trying to decode the sky, and every perspective lights up the puzzle a little more. If this journey through the universe's hidden layers left you hungry for more, hit subscribe and ring the bell. The cosmos has endless mysteries waiting, and together we'll keep pulling at the threads. Until next time, keep looking up and never stop wondering.